we are. So yesterday we started talking about alternative semantics of queries, and we examined two different such settings. The first was where we had databases in which the relations are bags, multisets, and then we focused on the containment problem for conjunctive queries, and I tried to tell you the history of this problem and the fact that it remains open. The decidability status of this problem remains open to date, although we know that the problem becomes undecidable once we add these two extensions to conjunctive queries that we examined before, namely unions or inequalities. Then we introduced the framework of probabilistic databases, and we focused on the simplest possible model, which is the tuple independence model. And our focus there was on the data complexity of conjunctive queries on tuple independent databases. And what we saw there was this beautiful dichotomy theorem by Dalby and Suciu, and I outlined the proof for the special case where the queries don't have self-joins. And we will see today this distinction between self-joins and or not having self-joins plays a role in the third topic, which is inconsistent databases. And the focus will be again on the data complexity of conjunctive queries in this framework, or in the framework of inconsistent databases. Now, let me say why I decided to focus on this topic. There are three reasons. One is that it's a topic that has been explored at great depth in the last 15 years or so. Second, as we will see, as I hope to show you, the results tie nicely with the other themes of this course, and in particular with finite model theory, and also the issue of constraint satisfaction and dichotomy theorems will also surface here. But there is a third reason, which was, for me, one of the main reasons, and this is to go back to the very first day of this course. In the third slide or so, I told you that there have been two main uses of logic in databases. One was to use logic as a database query language, and the second is logic as a specification language to express semantic restrictions, integrity constraints on the data at hand. And so far, we have focused exclusively on the first use of logic. It's been all about database query languages. But this discussion today will bring into the picture the use of logic as a language to specify integrity constraints. And integrity constraints, as I have already said, are semantic restrictions that the data at hand ought to obey. If you come from logic, it's the difference between having just all structures and all structures that are models of a theory. So far we have allowed our databases to be anything one can put. But what if we had some first-order theory around that restricts which are legal databases? That was not the original concept, that if you come from logic, that's how you should think about it. There was extensive study of integrity constraints from the very early days of relational data model through roughly the mid-'80s. And several people played a role in this, including Janos Makowski, who is in this audience. It started with key constraints and functional dependencies that were considered by code. And then, very soon, an entire zoo of different notions of dependencies, integrity constraints were studied: inclusion dependencies, joint dependencies, tree dependencies, multi-value dependencies, and so on and so forth. At some point, and I'm not exactly a good historian on this topic, eventually it was realized that all these different types of dependencies could be specified in fragments of first-order logic. And what came out of this was the consideration of these two classes of integrity constraints. Both of these are formulas, sentences of first-order logic. The first is the class of equality generating dependencies, or EGDs, which basically asserts that if a certain conjunction of atomic formulas is satisfied in the database, then necessarily two of these variables must be the same. And this class of dependencies, and now you can see why the name is equality generating, because the presence of the atoms forces an equality between two variables. Special cases include key constraints and more generally functional dependencies, which I will get to introduce separately in the next slide. And the second class, unifying class of dependencies, that subsumes joint dependencies, multi-value dependencies, and many others, is the so-called class of tuple-generating dependencies. These are now universal existential formulas, if you pull the quantifiers, the existential quantifiers to the front, that assert that if a conjunction of atoms holds, then some other combination of atoms must be also present in the database. And you may have atoms that involve additional elements, additional variables, different than those in X. And now, again, you can see the name that this is the dependency, a constraint that generates the presence of some atoms forces the presence of some other atoms, while before the presence of some atoms was forcing equalities. Special cases include the so-called local as view constraints and global as view constraints that have been extensively studied in the context of data integration. And I will get to define global as view constraints later on. Now, much of the work in the 70s until the mid-80s focused on the implication problem for integrity constraints. If some dependencies hold on your database, what other dependencies must also hold by necessity because of logical implication? And this was considered to be one of the main problems, if not the main problem, in database theory in the 70s and the early 80s. I mentioned before I went to for the first time to the database theory conference PODS in 1987. Jeff Ullman was an invited speaker, and he talked about the swan song of dependency theory and pretty much declared the subject dead. And actually, the subject has enjoyed a great revival. Indeed, it went out of fashion for much of the 90s. But towards the late 90s, early 2000s, the study of EGDs and TGDs was revived as in a different form, as the basic logical blocks to design schema mapping languages for formalizing data interoperability tasks, such as data integration and data exchange. In fact, much of my own work in the last 10 years has been on this topic. I chose to say nothing about this in this series of lectures because it didn't fit the theme of the other strands we have in this program. And another area where the study of integrity constraints has entered is the study of query answering over inconsistent databases, which makes the topic of this lecture. Now, let me introduce the class of actual constraints we're going to work with. All the results I will present here will be about key constraints, with the exception of one that will involve GAF constraints that will come later. And key constraints are a special case of functional dependencies. We have a relation schema R, and X and Y are sets of attributes of that schema. And when you write R X, 0, Y, this indicates a constraint that asserts that if two tuples in the relation R take the same values on the attributes of X, then they must also take the same values on the attributes on Y. And a special case of this are the key constraints, where Y is the set of attributes of R that are not in X. So the first one says that Y, the values of the attributes in Y is a function of the attributes of X, even though you don't have an explicit formula for this. And if this set of attributes is the complement of X, then you have a key constraint. Now, we can express this as equality generating dependence, of course, because, for instance, the functional dependency A, B, arrow D as an equality generating dependency tells you in a relation with attributes A, B, C, D, tells you if I have two tuples A, B, C, D and A, B, C prime, D prime, notice they agree on A and B, then necessarily they must agree on D. D must be the same as D prime. And the key constraint, A, B, arrow, C, D, is expressed as the conjunction of these two equality, or the set consisting of the two equality generating dependencies. So finite sets of equality generating dependencies can express key constraints and functional dependencies. So that's the example, the main example we are going to consider. Now, when in reality one designs a database, one specifies a schema, but also a set of integrity constraints, because again, this specifies the legal models. Sigma is the theory, as we would say in logic, and we are focusing on the models of that theory. An inconsistent database is a database I that doesn't satisfy sigma, and although so far I've been denoting my databases typically by D, here I will denote them with I to suggest that we are considering the case where the database may violate the integrity constraints. There is a discussion here that one could have about the contexts in which inconsistent databases arise. It could be that your database system doesn't support the enforcement of particular integrity constraints. A very standard way in which inconsistent databases arise is when you try to bring together data that reside in different sources, that each of these different sources may obey integrity constraints, but when you bring the data together, an integrity constraint that you had in mind is violated. It was enforced locally in the sources, in two different sources. You bring the data together and you have a violation. And in particular, this type of thing may happen in data warehousing and in the class of applications known as extract, transform, load. But I think the second one suffices. This is a very real problem. And industry has tried to solve this problem. And there is this engineering approach that goes by the name data cleaning. And this is a very pragmatic approach, engineering approach. It assumes that you have domain knowledge about your data. And then you get this database that is, as they say, a data database, violates the integrity constraints. And then based on the knowledge of your domain, and you have used heuristics to clean the data, and this entails adding, deleting, updating tuples in relations. And suddenly you produce, after this processing with the heuristics and using your deep knowledge expertise, you produce a clean database. Let me give you an example of what I mean by domain knowledge. Suppose that with every person is supposed to have only one social security number. And now you have a table in which the same person appears with two different social security numbers. But the social security number is a number having 9 digits, right? So if one has 9 digits and the other has 7 digits, it's reasonable as a heuristic to keep the one that has the right number of digits. But of course, if both have 9 digits, then often you have to make some arbitrary choice or use some other information. Roughly speaking, this is the main approach in industry, and I should say that major industry players offer such data cleaning approaches. IBM has a suite of data integration tools called the IBM InfoSphere, and the IBM InfoSphere quality stage has a data cleaning features. And the Microsoft Data Quality Services does something similar. And this is quite big business. Yes? Dana?
There's some worry that one algorithm would delete one tuple, whereas a different algorithm would delete a different tuple?
Absolutely. Absolutely. You are exactly right. In fact, the semantics, this happens all the time. And you can't even give precise semantics to this approach. It's really more engineering than science, because, as I said, often arbitrary choices have to be made, and that exactly is the point that you very correctly anticipated. Just to give you an idea, 10 years ago, IBM bought a company called SDR, SRD, Systems Research and Development, which was a company built by one of the most successful high school dropouts, Jeff Jonas, and paid 10 years ago $1.5 billion for a data cleaning company, right? And that has become part of IBM's business. So this is a big issue. Janos.
After 20 years in Israel, I discovered that I had 2 social security numbers.
There you go. There you go.
No, but the complications in clearing this were absolutely enormous because, I mean, these propagations and it actually happened because some clerk put in an 8-digit number and then it automatically was extended, but it was horrible. I mean, I don't believe that any engineering approach.
Thank you. Therefore, Janos says we need a scientific approach. And the scientific approach, which unfortunately the results probably will disappoint you here, is the approach of database repairs. And so database repairs offer a framework for coping with inconsistent databases in a principled way and without cleaning the data first. This is a framework that was developed, as we will see, by Arenas, Bertozzi, and Chomitsky some 15 years ago. I like very much this framework because it's a principled one, I believe. But as I will say at the end, it hasn't gotten much traction with industry, right? So this is still at the level of scientists and database theoreticians exploring it. But this is a very real problem. Perhaps this is these days one of the main problems addressing the data management industry. So here is the idea that Arenas, Bertozzi, and Chomitsky had in their PODS 1999 paper. Again, the setup is that we have a set of integrity constraints. We will focus here on keys, but any finite set from equality and tuple generating dependencies that I mentioned before could be such a set. And we have a database which violates one or more of these constraints. We say that another database, J, is a repair of the inconsistent database if 2 things happen. 1, J is consistent. And second, differs from I in a minimal way. So it is as close to I as possible. And of course, to make this precise, you have to spell out what do you mean by minimality here. And there are several different types of repairs that have been considered. There is a class of repairs that are called set-based repairs, where minimality would be, if you talk about subset repairs, it's a maximal subset, or superset, which would mean it's a minimal superset, or you can have symmetric difference repairs where you try to minimize the symmetric difference in the set theoretic sense. There is another class of repairs that consider similar types, but what you try to minimize is the cardinalities, the difference cardinalities. There is another class of repairs that tries to change the attributes as little as possible. So there you need a notion on the values of that under a particular attribute. And there is yet another class of repairs called preferred repairs. I have highlighted in blue the ones I'm going to talk about, namely subset and preferred repairs, and the subset are a special case of set-based repairs. But again, we are only seeing just a small view of what has happened in this area for the past 15 years. So here is the formal definition of a subset repair. So a subset repair of an inconsistent database is a subset. No, what do you mean by subset? Think of the database as a set of tuples labeled by the relations. So that's exactly what it means to be a subset. So relation by relation is a subset. J has to be consistent, satisfies the integrity constraints, and J is maximal with this property as regards the subsets, meaning there is no J prime subset of I that is properly containing J and satisfies the constraints. And from now on, I will use, for brevity, I will use the term repair to mean subset repair. Let's look at some examples. So let's take this key constraint. This says that the first attribute is a key, meaning that you have 2 tuples in your relation that take the same value on the first attribute, then they must take the same value on the second attribute. Clearly, this is an inconsistent database because A1 is paired with B1 and B2, and A2 is paired with B1 and B2. And from this you see that I has these 4 different repairs, where for A1 you can pick B1 or B2, and for A2 you can pick B1 or B2. And in general, you can see from this that even in this very simple scenario, you could have exponentially many repairs. So there are just too many repairs. And that will be the cause of the algorithmic complexity that we will encounter as we go on. Now, once they gave a definition of a repair, Arenas, Bertozzi, and Chomsky went on to give semantics to queries in the context of inconsistent databases. And their idea is we are not going to clean the database, unlike all the other approaches I mentioned before with heuristics. We're going to keep the inconsistent database around. But when we want to evaluate the query, we are going to consider all the repairs. Then the query comes, and what we do, we evaluate the query on each of the repairs. And then we take the intersection of the answers. And they call these the consistent answers.
Which might be empty.
Could very well be empty, and you will see an example, and that's why you won't be satisfied. they won't fix your problem. That's exactly right. That's exactly right. So the motivation comes from the semantics of queries in the context of incomplete information, which is yet another topic I didn't talk about, and possible welds. Notice also the similarity here with the probabilistic databases yesterday. With the probabilistic databases, we had a tuple-independent table, and that was a compact representation of potentially exponentially many actual databases. And then we asked the query on each database, and we summed the probabilities, right? Here, the inconsistent database and the constraint sigma represent the compact representation of the world of possible repairs, right? And what we do is we ask the query against each of these possible worlds and to take the intersection. Why is this a reasonable notion? Because it gives us a guarantee. The guarantee that it gives us is that no matter how we repair the database, when we ask the query and focus on the consistent answers, every tuple we will find in this intersection is guaranteed to be on every repair, no matter how we have repaired the database. So it's a conservative approach to semantics. It gives you this certainty guarantee that you're going to find it in every repair, no matter what repair you choose.
But that's assuming that, for example, the subset choice is the right choice for the notion of repair.
That is correct. So thank you. In the next example, you will see that this is really the natural choice. So let me make it, actually, since you asked the question, let me make it very concrete. When you look at key constraints, right? If you have violation of key constraints, if you add more tuples, you're making things worse. So the only reasonable thing to do here is to remove. And since I will focus on key constraints, that's the reasonable notion. So another way to think of this is that this notion is the notion of what we call the certain answers against a set of possible welds, where the possible welds here happen to be our repairs. So let's see this concept in action. Let's go back to our running example. We have one key constraint. The first attribute is a key. We have this inconsistent database. It has these 4 repairs. And let's look at the 2 queries. The first query gives us the projection of R on the first attribute. And now we evaluate this query on each of these 4 databases. Here we find A1, A2. 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 Therefore, we can say that the consistent answers of this query against this inconsistent database with respect to sigma is the pair A1, A2. But if I want to ask for the second projection, the Y projection, the second projection, then I get the empty set. Because here I get B1, but I don't get B2. Here I get B2, but not B1, right? So when I take the intersection is empty. So as Janos anticipated, yes, this is a conservative approach, right? And in particular, this will tell us, I can't tell you, there are no certain answers here, right? That's what this says. So this is the concept of consistent query answering. And there are three themes that have been explored so far. The two are algorithmic problems, and the third is system building. One is, what is the complexity of consistent query answering for conjunctive queries or unions of conjunctive queries or first-order queries? And there, depending on the type of constraints and the type of queries, anything goes, from polynomial time computability to undecidability. For repair checking, there is another natural algorithmic problem here, which is if I give you an inconsistent database and a consistent one, is it the second one a repair of the first? Does it pass this minimality difference test? So that's an algorithmic problem that, if you think for a moment, you realize it underlies the complexity of consistent query answering. There, typically, the results vary from polynomial time computability to CONP completeness. And then, in the attempt to take this theory and transfer it to practice, several academic groups have built prototype consistent query answering systems, and this work is still work in progress. So let's look at a simple case study which will also justify the use of subset repairs, or which I call repairs here. So I'm assuming we have a relational schema, and we have a set of key constraints, and for every relation we have just one key constraint. This is about the simplest scenario you can imagine. Every relation comes with one key constraint, and we have a Boolean conjunctive query. And then certainty Q sigma is the following decision problem. I give you an inconsistent database I. Are the consistent answers true? Meaning, is the query true on every repair of I? It's a Boolean query, so this is a decision problem, right? Now, in this scenario, it is easy to see that repair checking is in polynomial time. Why is that? Because if you have an inconsistent database I and a J, and you want to check that it is a repair, first of all, you verify that it satisfies the key constraints. This is a fixed set of constraints, so that can be done in polynomial time, in fact, in logarithmic space. And then it is going to be a repair if and only if, when you add just one tuple, it becomes inconsistent. So you examine one tuple at a time. This by the preservation under sub-databases of the key constraints. So this gives us a polynomial time, in fact, logarithmic space algorithm for repair checking. In turn, this implies that the decision problem certainty Q sigma is in CONP, because we are asking, is the query true on every repair? So this becomes, for every J, if J is a repair, is the query true, right? This universal quantifier for all J puts it in CONP. And of course, it's important that the test, is it a repair, was in polynomial time. Think of this in the negation. It is not it's going to be false if there is a repair on which the query fails. So we are guessing this repair. The repair is on polynomial size because it's a subset, right? And we verify that it is a repair. So this is in CONP. So now we have seen we don't know that we are in polynomial time, but we certainly are not beyond CONP in this simple scenario. So let me put down these three queries, and let's see what happens here. We have the first query says there exist x, y, z, so that RX, Y and S, Y, Z. So if you will, this is like a path query, except the labels are R and S. And 2 is there exists X, there exists Y, RX, Y, and SYX. So here we have X, R, S. So we have a cycle of length 2 like this. And the third query says there exists X, there exists Y, there exists Z, RX+Y, and SZY. So the pattern here is that we have X and Z, and Y is like a sink here with R and S and Y here. So we have these three Boolean conjunctive queries. And we are assuming that the first attribute of R and S is a key. So now the question is, what can we say about the certainty of these three queries? In other words, is it this query, each of these queries true on every database, on every repair? How difficult is it to decide this if I give you such an inconsistent database? And these queries were chosen on purpose because they exhibit very different behavior. Here is the answer of their behavior. The first query represents the best case scenario. What is the best case scenario? The best case scenario is that not only you can evaluate the consistent answers in polynomial time, actually you can do it with your database engine. And you can do it with your database engine because you can find a first order rewriting of the query. This means that you can find a first order sentence so that when you evaluate this first order sentence on your inconsistent database, then you get the consistent answers. In other words, this query is true on every repair if and only if the inconsistent database satisfies this rewriting. This is no longer a conjunctive query, and in fact you can prove it's not going to be a conjunctive query, but it is a first order query. So this is the best case scenario. In that case, you can, if that was the case with all the queries, this would be a nicely solved problem because we could do the rewriting, assuming, of course, you can find it effectively, and then use the database engine to answer the consistent answers. So I gave you here the rewriting. It is easy to verify. These two require proof. The third one, this is the sink, so to speak, with R and S, RX+Y and SZY. This one represents the worst case scenario. Remember, it's in CoNP, and this turns out to be CoNP complete. And the proof of this is not very hard. It's not hard at all, actually. You encode monotone 3-sat, where R stands for the positive clauses, X stands for a positive clause, and Y for a variable occurring in a positive clause, and this stands for the negative clauses and the variables that occur in a negative clause. And then you can show that it is a monotone 3CNF is satisfiable if and only if this query is false in the sense of consistent answers. The third one is in an intermediate state where it is in polynomial time, but is provably not first order rewritable. And this was a result of Jeff Eisen, whose name we will see later on. He's done a lot of work and very nice work on this subject. So the point I want to make with these three exams, which I will revisit, is that we are in an interesting situation here. We seem to have some kind of a trichotomy, right? We can have first order rewritability. We can have polynomial time evaluation, but not first order rewritability, or we can have CoNP completeness. So this, in turn, gave rise some 10 years ago to the question, can we classify the complexity of certainty Q sigma in this very simple scenario of subset repairs and key constraints? And a conjecture was put forward that if you have a set of key constraints with one key per relation, the simplest possible scenario, and Q a Boolean conjunctive query, then one of the following two holds. Either it's in P or it's in CoNP complete. And moreover, the dichotomy is effective, meaning there is a polynomial time algorithm to decide which of the two situations we have. So here again, the issue of dichotomy questions that we saw before in constraint satisfaction and yesterday in probabilistic databases and in query complexity arises in a natural way in the query evaluation problem in the context of inconsistent databases. Again, let me remind you the point of a dichotomy comes from Lardner's theorem that if P is different from NP, we have problems in this gray area, not NP complete, not in P. So the dichotomy conjecture tells us that certainty Q sigma is never here. It's either co-NP complete or in P. And to cut a long story short, after maybe a dozen papers on the subject by different people, last year in the PODS conference, which was in Australia, Paris Koutris, who's a student of Dan Shuchiu, whose name came up yesterday, and Jeff Wijzen from Belgium in Mons, proved that indeed there is a dichotomy, but so far they have only proved it for self-join free conjunctive queries. And remember yesterday, the little dichotomy theorem I showed you was for self-join free. And I didn't say anything about the general case. In fact, the general case is open, at least as of last week that I checked. So they proved that there is indeed this dichotomy between P and co-NP complete. In fact, you will see it's a trichotomy. And also from the proof comes out that the dichotomy is decidable in quadratic time. What is the tool? What is the key notion? They introduce a syntactically defined graph called the attack graph. The nodes of this attack graph are the atoms of the query. Now, the edges are determined in a complicated way. I'll flash the definition in the next slide, but I won't say very much about it. They are determined by the functional dependencies on the variables of an atom that are implied by the keys of the other atoms. You see, functional dependencies imply other functional dependencies. The classical example is transitivity. If you have that X determines Y and Y determines Z, then X determines Z functionally. So the atoms, the keys rather that we have on the set of integrity constraints may imply other functional dependencies, and you fix the edges of the attack graph to be determined by this interaction. The formal definition is this. In the interest of time, I won't go through the definition, but I will just point out that in the attack graph, which is a directed graph between atoms, you differentiate between two types of attacks, a weak attack and a strong attack. Now, if you take this definition and you run it in these three examples, you find the following picture. That in this case, the atom RX+Y attacks SYZ, but not the other way around. So in this case, our attack graph is just this. In this case, our attack graph is a cycle, but the cycle is weak, while in this case, the attack graph is also a cycle, but the attack is strong. And in fact, it's very strong. It's going strong both ways. You have to take this definition and run it on these exams, and that's what you get. So what they said is they started paying attention on the cycles in the attack graph. And they said a cycle in the attack graph is strong if it contains at least one strong attack. So here we have cycles, but here no strong attacks. This cycle is strong because it contains at least one strong edge. In fact, two strong edges. Now with this notion, so ignore the details. The important thing is that we have a syntactic notion of a graph with nodes, the atoms. And on this, we look at cycles, and we look at two types of cycles. Cycles without a strong edge and cycles with a strong edge. And it turns out that this is the secret to the dichotomy. They prove that if the attack graph is acyclic, then certainty Q sigma not only it's in p-time, but in fact it's first-order rewritable, exactly the scenario that we saw with the first example. If the attack graph has cycles but no strong cycles, then it's in polynomial time. But then it is not in first-order rewritable case. And if the attack graph contains a strong cycle, then you are in the CONP complete scenario. This is a very nice proof. Already this case of first-order, the second case of cyclic but not strongly cyclic involves Han's locality to prove that you are not first-order rewritable. So the technique that we saw in Anuse's lectures. And the rest involves reductions of some special cases where you prove separately as being CONP complete, similar to what we saw yesterday in the little dichotomy theorem. And then there is a kind of a non-trivial polynomial time algorithm for this scenario. So this is a very nice result. I want to illustrate it in another case, not because I was involved with this result, just because this was actually used in their proof as one of the stepping stones. So before Kutris and Weisen came up with this result, a student of mine, Nella Pima, and I looked at a very simple scenario. We just wanted to explain these situations here. So we looked at Boolean conjunctive queries with two different atoms, very, very modest. And also in the case where the queries were not first-order rewritable, because already there was a result by Weisen that had characterized first-order rewritability in this context. And then in this simple scenario, the criterion of cycles and strong cycles simplifies to this. If the union of the keys is contained in the intersection of the variables, then certainty is in polynomial time, otherwise CONP complete. And that's exactly what happens here. The union of the keys is x and y, which actually yes, that's exactly what happens here. The union of the keys. Otherwise, I'm sorry, this scenario and this scenario. Here we have the union of the keys. The union of the keys is x and y, which coincides with the intersection of the variables. Here the union of the keys is x and z, and it's not contained in the intersection of the variables. This result doesn't cover this case because we already assumed that the query is not first-order rewritable. So this is the Weisen and Kutris dichotomy theorem, and many problems remain open. The most striking problem, of course, is to generalize to arbitrary conjunctive queries, not just the ones that are self-join free. And notice that here, if you prove a result about conjunctive queries, you don't necessarily prove a result about unions of conjunctive queries. Because you see, a union of conjunctive queries can be true because the query is true in the first query is true in some repairs and the second query is true in some other repairs, right? So it's more complicated situation here. So the ultimate result in this setup would be to look at functional dependencies instead of just keys and the union of Boolean conjunctive queries. I think this is within reach. Maybe Kutris and Weisen will prove it soon. This seems to be a bit far away. What is the broader setup here? The broader classification challenge is to classify the complexity of certainty Q sigma, where Q is a first-order query and sigma is a well-behaved set of equality and tuple-generating dependencies. There are such notions that I'm not going to go here. But last year, in the pursuit of understanding this broader classification challenge, there was a very nice result by Gaël Fontaine in Leaks 2013. This is the journal version, who discovered an a priori and anticipated connection between consistent query answering in this setting and constraint satisfaction. And at a high level, Gaël Fontaine's theorem says that if the dichotomy theorem holds for certainty, consistent query answering, for a union of Boolean conjunctive queries and globalist view constraints, then the Feder-Vardy conjecture is true. In other words, the dichotomy holds for constraint satisfaction problems or for the family of the query complexity problems of conjunctive queries as we have seen in these lectures. What are GAV constraints? GAV constraints are the special case of tuple generating dependencies where the right-hand side has a single atom. No existential quantifiers in the single atom. In effect, think of GAV constraints as Horn clauses. Symmetry or some version of transitivity like this are examples of GAV constraints. And Gael's theorem is that for every relational structure B, for which you care about CSPB exactly the way Anus was describing this morning, you can find a finite set of GAV constraints in the union of Boolean conjunctive queries so that the complement of CSP is p-time equivalent. Well, here you need to use symmetric difference repairs because these constraints, the meaningful way to repair, you may add or you may delete. If you want to fix, if you had the symmetry constraint and you have a tuple violating it, you can repair this by either deleting the tuple or putting the symmetric pair. Anyway, this is a very nice result that tells us that in this field we encounter the same difficulties as with the constraint satisfaction. And so it's another way, another manifestation of how widespread, how many different ways the constraint satisfaction surfaces. OK, now for the last part of this talk, let's go to the pragmatics of consistent query answering. Already we saw before that we can have repairs where we can have queries when we try to evaluate the consistent answers, we get the empty set. So that certainly will not fix Janos's problem with the two social security numbers. This is the criticism of consistent query answering as a semantics approach as being too conservative. And the idea is we have too many repairs, and too many repairs result in too few answers because you take the intersection. When you start thinking about this, you realize that this comes from the fact that the framework treats all repairs the same. There is no differentiation between repairs. All repairs are equally good. So the idea that Staworko, Chomitsky, and Marcinkovsky had in 2012 was to make sense out of what it means for some repairs to be preferred over some other repairs. And this is the framework of prioritized repairing that incorporates preferences. And the idea is that if you have two tuples that conflict, you may prefer one tuple over the other in constructing a repair. This is reasonable because maybe this tuple comes from a more reliable source, right? As you try to integrate data, maybe one source is more reliable than another. Maybe you have some timestamps. Maybe every person is supposed to have one salary, and this person appears with two salaries, but the dates are different. And maybe the later timestamp is preferable. So that's the idea that they try to formalize. And here is the formal definition. An inconsistent prioritizing database is a pair I is the database, together with a binary relation on the facts, on the tuples in the database. And all you want from this relation is to be acyclic. And the idea is that if f and g violate one of these, so if f is better than g, then f and g violate one of the functional dependencies, and you prefer f to g. I'm defining here only for the case of functional dependencies. And this relation should be interpreted as saying between the conflicting facts f and g, I prefer to keep f in my repair as opposed to g, because it has a more recent timestamp. Yes?
I was trying to think of a situation like that, and I was considering maybe cost. It might cost more to eliminate one.
It may cost more if we have the cost explicit. Yes, that's a very good scenario for using this prioritized framework. Now, the preference relation, if you have it explicitly on the facts, induces a preference relation on repairs, and therefore we can focus on optimally preferred repairs and then make this our collection of possible wells against which we're going to ask the query. So this is the notion now of a global improvement. suppose I have an inconsistent database and two different consistent subdatabases. Then we say that J is a global improvement of K if, let's take these two databases and split them this way. In the intersection, we are fine. Now we look at the part J minus K and K minus J. And what we insist is that for every fact that is in K but not in J is dominated by some fact in J minus K. So we prefer J to K because every fact in K minus J is dominated by some fact in J minus K. And in that case, we say that J is a global improvement of K, and then a globally optimal repair, from now on I'm going to call them G repairs, are instances that are consistent and have no global improvement. So they are optimal in the sense of global improvement, which is induced by the prioritizing relation. And you can verify that every G repair is a subset repair of I. So now, instead of looking at all repairs, we are going to look at G repairs. And let me give you an example of this, to which I will return. We're in a university, and we're in a good university, where every instructor, every term teaches only one course. Okay? And also, this university doesn't allow courses to be co-taught. And that means that for every course and every term has only one instructor. So this is the meaning of these two functional dependencies. And now we have this inconsistent database. For instance, F1 and F2 conflict because we have different instructors for the same course on the same term. And the same thing for F3 and F4. F5 and F6 are conflicting because they violate this one. Instructor and term, John is not supposed to be teaching two courses, programming language and databases, right? And finally, F5 and F7 are conflicting because programming language in Spring is supposed to be taught by only one instructor. And now you can verify that K is a repair of I, clearly, but J is a preferred repair because you see, what we have here is that F2 is preferred to F1, and F4 is preferred to F3, and F5 is in both. So that's an example to which I will return. I will return to this. Now, let's go back and see what has happened. So we have succeeded with this framework to cut down the space of repair. So in principle, we're getting more consistent answers. But now the other problem, which was for us easy, may become hard. What was the other problem that was easy? Repair checking. We saw that for functional dependencies, if I give you I and J and I ask you is J a repair of I, that you can do in logarithmic space. But here it is no longer the case. It is easy to see that it's in CoNP, but actually Staworko, Chomitsky, and Marcinkovsky in 2012 cooked up a set of 4 functional dependencies on a relation of RET8 such that G repair checking is CoNP complete. So this is a bit disappointing, right? Because you see, we try to get better pragmatics, and then another algorithmic intractability emerged, even all the way down to the level of repair checking, which underlies the consistent query answering. So the question then is, can we classify the complexity of G repair checking so that we know what's happening here? And that's the work that Ron Fagin, Benny Kimmelfeld, and I did at IBM. This was back in 2014. Paper was published in 2015. Benny Kimmelfeld now is a professor at Technion in Israel. And we have a dichotomy theorem for G repair checking when you have a collection of functional dependencies. And this says the following. You have a set of functional dependencies. As I said, this set of functional dependencies imply other functional dependencies. And then you look what functional dependencies they induce on each of the relations of the schema. If sigma induces a single functional dependency or 2 key constraints on every relation, then the problem is solvable in polynomial time. In all other cases, it's CoNP complete. and the dichotomy is effective. In fact, there is a linear time algorithm. This is a data complexity result. The constraints are held fixed, and the input consists only of the prioritized database instance and the candidate database, and the question is it a G repair? Here is an illustration of this dichotomy theorem. Let's take course term and instructor. If we have this pair of functional dependencies, course term determine instructor and instructor term determines course, which is the scenario of the example, we have two keys, and therefore it's in P time. If we have all we have in the database, the instructor determines course, it's in polynomial time because we have one functional dependency. But if we have something like this, that's a boring university. Every course is always taught by the same instructor, and every instructor always teaches the same course, right? In that scenario, checking for global repair is COA/NP complete because we have two non-key functional dependencies. A word about the intractability. Remember yesterday when we did the outline of the proof of the little dichotomy theorem, we had one query that was difficult. We proved it independently. Dalvi and Suciu proved independently. I showed you the proof. And then everything else was proved intractable by reduction from it. Here, things are more complicated. It turns out you have to examine 6 basic sets of functional dependencies for a ternary relation. These are the 6 on a ternary relation ABC. These are the 6 cases where it's not 2 keys or 1 functional dependency. For each of them, you prove that G repair checking is COA/NP complete, and then you do the proof of intractability for an arbitrary set using a case analysis and distinct reductions from each of the 6 cases. So it's a bit more complicated than the other one. And then separately, you have to prove the tractability case. So this is a quick outline. I'm almost at the end. We have several open problems for preferred repairs. What I showed you was only the case of we want to see an arbitrary set of excuse me. What remains completely open is to the complexity of repair, of consistent query answering in this context. So G certainty means compute the consistent answers when your set of repairs is the set of globally optimal repairs. What seems to be the case here is that we will end up with a trichotomy theorem between pi to p complete, COA/NP complete, and P. The pi to p complete will probably arise from the cases where the underlying G repair testing problem is COA/NP complete, of which we just saw there are plenty. When you look at the proofs of these intractability results, you see that what makes things difficult is that this preference relation is given to you semantically. It's part of the database. But in reality, in the applications one can think of, typically this preference relation is specified syntactically. Bigger cost, as Professor Scott said, or more recent timestamp, or some other such information. So there is an interesting question if there is a useful language for expressing preferences for which these 2 problems, G repair checking and G certainty, are of lower complexity. There is another line of work that I've been doing with colleagues at IBM Almaden, and this is to create a declarative framework, declarative languages for entity resolution, and which is the problem related to data cleaning, identifying if 2 records represent the same record. 2 names are misspelled. The first name has become the last name, and so on. These are usually done in a very engineering approach using machine learning and a whole bunch of other algorithms. And we have tried recently in the last 2 years to work on a declarative logic-based framework for this. We also wanted to incorporate preferences, and we have gotten some good results when we have the preferences specified syntactically, but we have not carried it out with this investigation. So let me close with some reflections on what we have covered. This is the summary. We have focused on logic and database query languages. our focus was on these three problems: query evaluation, query containment, and query equivalence. On the third lecture, we saw this work on acyclic joins, tree width, and the Atzerias-Groy-Marx theorem with the tight bounds on the size of natural joins. In the last two lectures, we have focused on the alternative semantics in the context of back databases, probabilistic, and today inconsistent databases. The emphasis, as you have seen, has been on this triadic relation between databases, logic, and complexity or decidability. I don't want you to think that this is an exhaustive list of topics in database theory. There are a whole bunch of things that I have left out. I mentioned before that automata theoretic techniques are very important. I didn't cover them. Didn't say anything about the implication problem about database dependence. This is very nice and classical work. Incomplete databases is where you don't have a value and you put a null value, and there is a lot of work there. This whole area of information integration, data exchange, data warehousing has not been covered. These are all areas in which logic has played a role. Data privacy and security is a timely and important topic. Logic has not entered very much in this, but there is room for this. There is data provenance, but it's in blue because we'll close this bootcamp with a guest lecture by Val Tannen. And finally, I have focused entirely on the relational data model, but there is many alternative worlds outside the relational data model: semi-structured data and XML, graph databases, web data, and the like. But I hope to have convinced you that logic and databases are indeed inextricably intertwined, and this explains also the logo we came up for our program. This is the engine of logic, and here is the natural join, and that's the descriptive complexity. This is the quantum, and this is the probability. And that's what we hope to get out this semester. So thank you very much for your attention. Questions? Yes.
So, as I understand it, there's sort of a conceptual separation in getting these answers to inconsistent queries. In the first, you've defined somehow a class of repairs,
yes,
either all of them or some preferred ones or something. Yes. And then you ask, what are the answers to this query in each of these?
Yes.
And intersect.
Yes.
Pragmatically, wouldn't it be sometimes more useful to not separate things? So, for example, if I want to know Janusz's birthday, the Social Security problem shouldn't affect that. The database will presumably have only one birthday for Janusz. So I shouldn't have to bother repairing the Social Security problem before I try to answer the question about birthday.
So in this particular example, the consistent answers will give you the right answer.
They will give me the right answer.
Yes.
But they'll make extra work, right? Because I'll have to first create all these repairs.
Yes.
And then verify, yes, same birthday every time, actually with. Whereas I could, at least as a first attempt, given the query, say, never mind about the repairs, Social Security, look at his birthday. There's only one birthday. Done.
But then you are just asking the inconsistent database.
Yes, that's right. The question is, when can I ask an inconsistent database without having, what queries can I reasonably ask?
Yes, so
without having to go to the repairs?
Yes, in some sense, this is answered nicely in the Weisen and Kutry's framework. In some sense, this is the case where the queries are first-order rewritable. Because in that case, and the criterion for the self-join free queries is you build the attack graph and you determine whether that is acyclic. And that's a quadratic algorithm. So in this scenario, we have a good answer. And this is really the best we can hope for, that we don't even have to implement any algorithms outside what the database engine offers us, right? We just have to rewrite the query. So this is the best scenario. But beyond that, in other scenarios, I don't have a good answer to give you. Excuse me, Janusz had the question and then.
I wanted to make a remark that, repairing is an old problem in philology. You have many copies of Homer's Odyssey, and you
Yes.
want to figure.
Yes.
And people have developed a criterion which is called Lectio Difficilior, assuming that the scribe who is copying is not as intelligent as the author, and he will make a mistake which makes the text easier to understand than the original. On the other hand, Google, if you mistype, or if you look for speckle, you get all kind of alternative spectrum, spector, but they don't want to look for speckle because they are sure you must be wrong, and they repair you. So I've tested this. So application is fine, but these application domains are very complex. I mean, just comparing the two situations, and it's not clear. It's not clear what you ought to do.
Well, and as I said, the people, big companies buy smaller companies who develop domain expertise in a particular area, and they can figure out, do the data cleaning as accurately as they can. Right? By the way, since you mentioned that the problem is old and it was solved somehow in philology, this idea of repair is also related to belief revision. Right? Belief revision in AI, right? So this is where some of this originated. There was TJ and I think, well, here's the question.
It's kind of a long shot question, but I was just wondering, in the second case where the problem's NP but not FO rewritable, is there perhaps a natural rewriting to use fixed point logic or something?
That's a good question.
So if your database engine happened to support recursion, you're still good.
Okay, so I can tell you, I don't know for generality, but I do know the case of two atoms. In the little paper that I had with my student, the case of the two atoms, we used a Mintis algorithm, which is finding maximum independent sets in claw-free graphs. Now, there is Victor Dalmau was visiting me last spring, and we revisited this, and we also saw that you could do it by 2SAT, by reduction to 2SAT, and 2SAT is something you can do in data log. I mean, so that would be, you may be on the right, but it's a good question. I don't think Kudris and Weisen have looked at the descriptive complexity of this. That's a good question. Val?
Yeah, I was just going to, it's actually related to what TJ said. So the really remarkable fact about the first case, FO rewritable, is not just that it is FO rewritable, but that in fact you can transform this whole thing into a self-repairing system. Yes. That is, you can implement an algorithm that actually can test, uses this quadratic time, and can test if you are in that case and in fact produces a query. It's a little less important whether that query is actually expressible in standard SQL. I mean, of course, it is important very practically, but it is important that you can actually express it in something that can be easily implemented automatically. Yes. The user who just threw out the query there doesn't want the system to come back to her or him and say, well, I can enumerate all these repairs for you and stuff like that. They just wants the answer. So I think TJ is right on the money for the other.
Yeah, no, I think this is a very good. This is a very good. But even in the CoNP complete case, I should say that you can still solve it. There are several different approaches. Bertozzi and students and collaborators have used answer set programming, which is basically you can write the problem of computing the consistent answers in disjunctive as a disjunctive logic program, and then you look at the stable models of this program. With some other students, we have worked on the scenario of that we looked here, one key per relation. And we did a reduction to 0-1 integer linear programming, and we got good results. And I was in the SAT conference in July, and I gave a talk along these lines, and people are very interested in trying to use SAT solvers for the third case. So there is this. I present the results here at the level of just the theoretical exploration of the complexity. But I didn't tell you anything about the prototype systems. Unfortunately, I have to be honest with you, the industry has paid zero attention to the work on repairs. I mean, no system.
Well, but that's because, you know, they're not sympathetic to the fact that we're trying very hard to remove the self-join free requirement, yes, about which they don't give that much of a, yes, right? On the other hand, if we would consider self-join-free conjunctive queries with some aggregation, for instance, I think they would pay attention.
Yes.
Especially if we can somehow find algorithms that can compute the results of those aggregations under all the pairs and so on, maybe approximately. I think that would be much.
So the only case of first order rewriting with aggregation is there is some preliminary work in the PhD thesis of Ariel Fuchsman. And this is the thesis I sent you guys yesterday.
But that's 10 years old at least, right?
2007, yeah.
So it's remarkable.
Professor Scott, yeah.
Just a quick observation and then a question. I have 2 birthdays. I was born just after midnight, and the doctor unfortunately wrote 10th of October on the birth certificate, but my mother insisted that it's the 11th. And it's unfixable. But the question was, in your experience, what size databases do you imagine this is very practicable for? I mean, it seems like there'd be a combinatorial explosion.
Oh, there is a combinatorial explosion. Yeah, this framework, yeah. The people who do data cleaning dealing with huge databases, for instance, insurance companies that try to determine that the 2 records are of the same individual, where they try to trace for accidents that have taken place in other states where the name may have been misspelled. I mean, this is a huge application. And then they're dealing with very large databases. Yeah.
Are there contexts where it makes sense for the distance measure that you were speaking about to actually manipulate inside tuples? So from what I understood, the ones that you listed, they didn't include things like edit distance on the strings.
No, yes. In the very beginning, I mentioned attribute-based repairs. Okay. And these are exactly the class of repairs, and Jeff Eisen has done a lot of work there. This assumes that you have a data type on which you have a reasonable notion of a distance. And he has some work that nice results, but again, he has not gone very far there. I mean, yeah. It makes perfectly good sense. Well, thank you again.
Pay attention from now on.